Hey everyone, Chang here and welcome to my channel. Now for this video, it's going to be a little short. I want to think of it as sort of a prelude or an introduction to the idea of proof. Now, I did show some proof before in this channel, but today I'm going to focus on the symbols of proof. Here's the thing. A majority of the time when we are studying math, symbol means to do some form of calculations. The only time where symbol doesn't actually mean any calculation or as a name of anything is in proof. Actually, a majority of the symbols in proof represent shorthand for regular everyday English phrase or sentences. So there are many, a whole tremendous list of it. You can look it up online and you'll be super overwhelmed. But in all honesty, there's 7 categories, 7 sort of symbol, a little more, that I see as the most common when introducing proof. Now, here's the thing about proof though. There's no set way of writing a proof. Some people will be more wordy, some would love to use more symbols, right? There's no right or wrong. So keep that in mind when you encounter proof, encounter mathematical, sentences. Because guess what? The way one person writes it and the way another person writes it could be completely different, even if they're saying the same thing. So here are some common ones right here. We have these weird looking symbols. The first one looks like an upside down letter A. You have an E that's backward. You have the 3 dot that is a brainiac kind of symbol, if you know DC Comics, right? And then you have the arrows that could have 2 different variations. You have ST or this sort of lower, I wouldn't say lowercase, but it looks like a rounded edge E that's again in the opposite direction. These 2 are actually meaning the same thing from what I can tell. And then you have this one where it's going to be the backwards E with an exclamation mark. Then the regular E that's like a rounded edge. Then you have your 2 arrow on both sides, which can be seen in these 2 ways. Now, these are the most common. They're not conclusive in any way. But from my understanding, here's what each and every one of these mean. The first one is usually for all, which is a good thing because, just think of the backwards A as a way to memorize it, or for every. So basically, if you're talking about a group, it's talking about everything in that specific group. That's what this means. The second one is there exists. Okay, so maybe the E will be a good factor to help you remember. There exists. That means out of all the group, there is something. It could be one, it could be more than one that fits whatever criteria you're arguing. There exists, right? This one here is usually the one that you really want to see, right? Because this usually means the end of something, right? This is therefore, or in conclusion, if that makes it better. Conclusion. Okay, so there's that. Now this one, I guess you could say sort of, once again, these 2 are just interrelated. Some will look like this, some will look like this. This means implied. So that means because of something that implies the other thing might be true or false, just it implies a specific consequence, right? This one, I like this one a lot better. I've seen this as more common, but I've also seen this used as well. This stands for such that. All right, blah, 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 such that this is the case. Blah, 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 such that, conclusion or whatever. Usually conclusions therefore, but some people say such that, right? So we have that, and once again, I prefer this. I've seen this used a lot more, but sometimes this, so just be careful when you see this. Don't get this mixed up with this, which I'm going to introduce just in a second. This and this are very similar, but not exactly the same. The exclamation mark you can think of, it means a special case. This actually, to help you memorize it, if you think of it as a special case, there exists one. Okay, or exists only, different variations of that, right? The first one here, there exists. I mean, there could be one, there could be multiple ones that fit the criteria you're looking for. Here, on the other hand, there's only one. Okay, there's only one special situation, special case whatsoever. That's what this one is. So this gives you a slightly bit more information than this one, but basically both of them still says there exists, right? This right here is element, or is an element, is probably more correct. So oftentimes when you're talking about proof, especially when you're talking about groups of numbers, right? The group of number might have some sort of criteria or some category for it to be counted in a group. So for example, even numbers, it has to be divisible by 2. If it's not divisible by 2, then it's not an even number. So is an element means that it is part of that specific group or category or whatsoever, right? So for example, 4, you would write 4 is an element of, and then whatever group you say, you could even say even number, or sometimes problems or proof will have like a specific name for that group, right? And so that's saying that 4 is part of that group, right? One of the individuals in that group. And then of course you can have a bunch, or you can have a small group inside, you know, a bigger group. Now, this one and this one is slightly different. This is one direction. Because of this condition, I can conclude, or I can it implies that this other condition happens. But that doesn't mean that if you had that like end result condition, that the original condition is always true. This, however, is saying that's the case, right? It implies both ways. Implies both ways. So if one condition is true, then the other one's condition is true, and vice versa. Whereas this one, because one condition is true, the other one is true, but it doesn't guarantee that that one is true, meaning the original one is true. So that's a slight difference in variation. So be careful of that. One gives you substantially different information, right? This one is wonderful because that means you immediately know that both conditions are whatever it is. Whereas this one, it just means one implies the other, but not necessarily the other way around. So here's the 7 of them. And what I'm going to do next is I'm going to write, I guess you could say, math sentence in these symbols, and then we're going to translate them so you get used to seeing these kind of symbol. And then afterwards, I'm going to do one proof that I've done already, and I'm going to link the description in the video itself. But I'm going to use more mathematical symbol and less, I guess you could say, sentences or explanation, and hopefully you guys can see. All right, so here's our sentence. Doesn't look like a sentence at all, huh? But yeah, this is our mathematical sentence. So what do we have? Well, we have all these weird random symbol, and afterwards you're probably going to hate me because one, I'm a jerk. Just plain and simple. No arguments there. The other one is that this sentence actually says something so blatantly obvious to us that it makes no sense to make it so confusing. But, you know, for people who, I guess you could say, specializes in proof, loves proof whatsoever, they want to be as technical as possible. And it makes sense because math is a technical subject, right? So they would do something like this. I mean, not everyone, you know, normally they would just write it in a sentence, but this does save you a lot of time if you get comfortable in just writing mathematical symbol. So what does this say? Well, first and foremost, let's just look at this symbol. And if you guys remember in the previous section, I mentioned that it looks like an upside down A, so we can always at least remember that it means for all or for every. So for all x, or in this case x is a variable, right? As an element, remember this is that rounded e, so it's saying x is part of this group right here. Now this right here, this symbol actually means a specific group. It is a name of a group, integers, right? So it's saying for all x, where x is an integer, x is an integer. And as you can see, as I'm starting to write it out in English, right, you can see it gets a lot tedious, it's a lot longer, but at least it makes more sense in a regular point of view. So for all x, where x is an integer, right, this one, the backwards capital E, hopefully you guys can remember, means there exists. It could be more than one, or it could just be one. So there exists y, which is another variable, y, right, where y is a, and this one is again another sort of name symbol that you sort of just have to know. And I did make a video about these guys. This is integer, this is real number. So that incorporates all integers, all fractions, you know, rational numbers, and numbers that are not able to be written as a fraction. So for example, pi, e, so on and so forth, right? So where y is a real number, now out of all the proof symbol, this is my favorite again because it's so easy to at least remember, and I approve of this because this just means that you're just writing shorter, and at least it's not just so weirdly shaped. So where y is a real number such that y is greater than x, and I can keep it at that, or I can just write it all out, greater than x. Okay, so let's at least understand what this is talking about. So there's that entire string of symbols that looks super scary, and when we translate it into regular English, we have for all x, where x is an integer, there exists y, where y is a real number, such that y is greater than x. So what does that mean? Well, x is an integer. Integer itself is basically all the negative whole numbers, 0, and all the positive whole numbers. Okay, so for some whole numbers, positive, negative, or 0, there is another number in the y, where y is a real number. Basically, there is another number that's a real number, meaning that it could be a whole number, it could be 0, it could be negative whole numbers, it could be fractions, right? Or decimals, depending, and it could be just numbers that you can't write it as a fraction in any way. So there basically is some arbitrary number that's gonna be bigger than x. So any whole number, you can always find another number that's bigger than it. That's all this is saying, right? It looks super complicated. No, it really just abnormally simple. All it's saying is that if whatever whole number you have, I can always find another one that's bigger than that. Obvious, but yeah, that's what we have right here. This a very complicated looking symbol for such an obvious statement. Now, not all of your proof is going to look like this, although it is actually kind of funny once you get used to it to see that, oh, really? You can just, point out a more obvious statement. I'm going to go over one where we're actually going to be proving something. And I went over this before. It's the square root of 2, and the most common proof, you can see it anywhere, is the fact that square root of 2 is an irrational number, meaning that it cannot be written as a fraction. And I went in depth on proving it just by, I guess, word of mouth, explanation, and going step by step on that. So I'm going to put a link in the description down below. I'm going to go over the proof again, except for this time, I'm just going to use all mathematical symbol. And maybe some, words here and there. And so you guys can see how it can actually save you a lot of, I guess you could say, time. You're not writing an actual essay if you get comfortable using these symbols. So let's look at that. All right, so here we have it. We're going to prove square root of 2 is not an element of Q. Now, if you guys remember, Q right here, this capital Q, fancy looking Q, right, is the symbol for the entire group of rational number. Basically, the symbol for the entire group of all the numbers that could be written as a fraction. To say that square root of 2 is not an element of Q means that it is basically irrational. Now, remember that when I first proved this, and I'm going to leave a link in the description down below, it's by contradiction. And that's what we're going to do as well. But this time, I'm just going to write a majority of mathematical symbols, and hopefully you guys can follow along. I will be talking as well, so you guys aren't just left in the complete dark, but you guys will see how me talking a whole bunch but not writing a lot is the sole reason why people love using mathematical symbols for proof, for better or worse. All right, so we're going to assume P and Q as an element of the integers, right, where P and Q are coprime. Basically, what this means is that P and Q are simplified in relation to each other as the smallest possible. They don't share any number that can be divisible by each other, or, basically is as simplified as possible, right? So we're going to assume that P and Q exists in the integer, and they are coprime such that P and Q equals square root 2. Okay, this implies P squared equals 2Q squared. Okay, and I am deliberately jumping steps because the sad thing about proof is that it's based on the discretion of the author itself. I could easily, and if I'm nice, or if the author's nice in any way, go exactly step by step. So the step that I'm missing is that I squared each side. This is going to be p squared over q squared equals 2. And afterwards, that implies that when I move q squared over, I would get this. So that's two things that are sort of left out. But the sad reality is proof, they assume you can follow at least certain basic step. And that can be detrimental sometimes because, you know, sometimes you can't, right? It's not blatantly obvious all the time, but that's the sad reality of it. So this implies that, which implies, and once again, you can start jumping steps, or hopefully you guys will see that p is an element of even number. Okay, so basically that's saying that p is an even number. Now, because of this, right, so we say that there exists m as an element of the integer such that p equals 2m, which implies, right, 4m squared equals 2q squared, which implies q is an element of even number. And I'm jumping steps again, right? So basically what happens is, what I'm saying is that there is some number m that's an element of the integer such that p equals 2m. And the reason for that is because p is an even number. Basically, I'm saying that p can be written as 2 times some other number because p is an even number. Therefore, that implies that if I substitute p in relation to this guy up here, right, I would get 4m squared equals 2q squared. And that implies basically a similar reasoning, right? As we jump again, we divide 2 on both sides, you get 2m squared equals q squared, which also implies that q squared is even, which implies that q itself is even. So once again, jumping steps, right? Just so you guys get a little bit more familiar with this. And this is, I mean, this is already like showing you certain steps, certain proofs they don't, which is not very nice, but we'll see. All right, so there we have it. Well, since p is an element of even number, q is an element of even number, but we initially assumed that p and q are coprime, meaning that they're as simplified as much as possible, we run into a contradiction. So usually someone would say contradiction, and then I think there is a symbol for that. Don't quote me on that. I believe there's a symbol for contradiction, but there might not be. So here it is. And therefore, now something that I didn't quite introduce, but I'm hoping that you guys got, is that for the 7 symbols, 7-ish symbols that I introduced in the beginning, if you draw that symbol and you cross it out, like this one right here, it just means not, right? The opposite. So there does not exist a p and q as an element of the integer such that p over q equals square root 2. Basically, it's saying that therefore there's no such thing as one where you can actually write square root 2 as a fraction or as a rational number, which is what we tried to prove in the first place, right? So this whole thing right here is technically your proof. Now, this is sloppy, right? A lot of the proof that you guys will see is going to be a lot more cleaned up than this. So they might even take out more steps, but they just want to make it look nice. And that's the sad reality of it, right? Proof, they want to make it look nice. It's supposed to be easy to follow along as well. So the author, whoever wrote the proof for you to read, should know to balance that. But once again, it's up to their discretion. And I've experienced people who are super mathematical geniuses who can read numbers in the sky, whatever, but when they're trying to write out proofs and they're trying to explain, I guess, stuff to me, it might go over my head because I'm not at that level. So that's the same with proof. If they write stuff and then all of a sudden you aren't seeing the hidden steps, it could be super confusing. And hopefully you won't encounter that, or if you do, you're at least at the par of being able to infer what they're saying. If not, then the lovely thing about it is that proofs aren't so easy to just come up with right on the bat. Usually, like for example, this proof, there's a million different, I guess you could say, format ways of people showing this proof. So this is just my sort of 2 cents on, I guess you could say, strategies on dealing with proof. If you don't understand one specific proof one way, look up, especially in the digital age with, you know, online and all that stuff, there's bound to be other people who proved it the same way using different symbol, or maybe including the steps that the original author left out. That will help you understand it. All right, so there we have it. We have 7 symbols, 7-ish symbols of proof that you would normally see. Once again, proof is up to the discretion of the author. They may use symbols that you've never seen before, and that's the sad reality of it, is that we're all super lazy. instead of having to write it all out, we would rather use symbols to shorthand it. Some of them are easier to understand than others. Luckily for us, these 7 are somehow, I guess you could say, agreed upon. 80 to 90% will use one variation of the symbol or another, right? And all the other ones, the special ones, then hopefully they included some, I guess you could say, remarks on what they mean. Usually they're nice enough to do that. Sometimes they're not, and then you're kind of screwed. So what do we do about this? Here's the thing, it's like any other, I guess you say, new language you're going to learn. You're going to rely on, I guess you could say, a glossary or a dictionary, right? Not the new ones where you just enter the words. The old one where you actually have to look things up. My recommendation is that as you start getting more and more familiar with looking at proofs, right? The ones where they are not so nice in typing out or writing all English words, where they start using these symbols, have a glossary of the common ones that you would normally encounter. And of course, every now and then, depending on the textbook, they have special ones, and you can put that in your glossary as well. Have those ready. Every time you see a symbol, eventually, by just always comparing, oh, this means for all, this means for, or there exists, so on and so forth. Just by comparing it back and forth again and again, eventually it gets ingrained in your head so that when you see the symbol, you read it almost like a regular English phrase. That's all I can really say about that, right? Is it going to get easier? Of course, but it does take a little practice, a little patience. But after that, you will definitely reach a point where you look at something like this, and especially the previous one where it was just an absurd sentence, but it looks very scary, and it won't after a while because you can immediately translate, you know, like a second language or whatsoever, the sentence into regular English, and you will understand exactly what they're saying, exactly what they're asking. Once again, these symbols, not real math, just short-handed English. Thank you for watching this video. As we introduce these symbols more and more, I will use more generalized one, but I do want you guys to get comfortable with it because this is unavoidable. All right, see you in the next video.